Hi, I'm Matt, and in this video we're going to discuss how to evaluate limits that are equal to positive infinity, negative infinity, or limits that don't exist at all. So before we discuss how to evaluate limits of those forms, first I need to discuss what it means for a value to be undefined. So first off, I want to stress, and I did this in a previous video as well, that being undefined is very different from being an indeterminate. To be undefined means that when we evaluate that function at x equals a, we find that that a value isn't even in the domain of that function we're evaluating. So f of a does not exist. And in this video, I want to stress before I go forward, we will only be considering real numbers. So let's talk about some functions that the domain isn't the entirety of all values. So here are three common examples. So the first function is k over 0. When k does not equal 0. Anytime we have a number divided by 0, it's not going to be defined. The reason I'm not including 0 here is 0 over 0 is an indeterminate, which is again something different. We also have the natural logarithm of g for g is less than or equal to 0, because the natural logarithm of a number is only defined when it's greater than 0. So anything else would give an undefined. And lastly, the square root function, or the square root of m, is undefined when m is less than 0, because we can't take the square root of a negative number. Again, some of these functions may be defined over complex numbers, but again, we're only going to be discussing real numbers for the purpose of this video. So now with that out of the way, we could discuss how to find the limit of f of x when we have a function that's undefined. So if you watched my first video with an introduction, we discussed what to do if it was piecewise. In another video, we discussed what to do when you obtain a real number by direct evaluation. Then we've also talked about how to evaluate an indeterminate, and I said that there was one more arrow. That arrow leads to when we plug in the value of x equals a and we get an undefined result. And we're going to have to treat this differently than we did the other two cases. When we obtain an undefined result, what we're going to want to do is we're going to want to graph the function, or at least make a quick sketch of it, to determine the behavior at that point. And just as we've done when we've graphed functions in the past, we're going to observe what value is approached and confirm that it exists, or if it doesn't. And if it does exist, we're going to want to say what it is. So now that I've gone through this whole scheme over multiple videos, I want to point out that this flowchart only terminates at 3 points. The first is if it's piecewise, we graph the function and then we look at the graph. That's one way. Another way is after evaluation, we eventually obtain a real number. The other way is if we initially gone undefined, again, going to the point where we determine if it exists and what we get. So again, these are the only 3 places we can stop. We can never stop taking a limit when we're down here, because we say it will always flow back here as we obtain an undefined result or we obtain a real number. So now, how specifically do we evaluate a limit when direct evaluation gives us an undefined result? So just as we've done in all my other videos, we're going to start by writing the function, and then we're going to plug in the value for a and just show it's undefined. The reason I say to do this, even though you might just be able to see that by looking at it, is going forward, you don't know what type of limit you'll have, so it's always good practice to start off by just trying to evaluate it directly. Once we get an undefined result, we're going to want to draw or plot a graph of the function in that region of interest. So since we're taking the limit as x approaches a, we don't need to sketch the whole graph, but we're going to want to sketch it in that region around x equals a. After that, we're then going to want to observe what value is being approached from the left and what value is being approached from the right. If those two are equal to each other, the limit's going to be that value. And if they are different from each other, we're going to find that the limit doesn't exist. In particular, when we get an undefined result under direct evaluation, we're going to see that the limit either doesn't exist or it's positive or negative infinity in most cases. In fact, I can't think of any case where this wouldn't be how it works. And lastly, once we figure it out, we're either going to write the value it approaches, so the limit as x approaches a of f of x equals L as we have before, or we're going to then put a d and e after it if the limit doesn't exist. So with that, let's try some examples. For our first example, we're going to evaluate the limit as x approaches 1 of 1 divided by x minus 1 squared. So as before, the first thing we're going to do is write our function 1 divided by x minus 1 squared, and we're going to plug in x equals 1. Doing so gives 1 divided by 1 minus 1 squared, which of course gives us 1 over 0. So now we have shown that our result is undefined, and from there we're going to try to graph the function. To do that, I'm going to draw a graph, and we're going to look around here, and I'll call this point x equals 1. So let's start at 0. When we plug 0 into our equation of 1 over x minus 1 squared, we're going to get 1. When we plug in 1/2, we're going to get 4. If we plug in something very close to 1, such as 9/10, we're going to get 100, which this isn't to scale, but might be all the way up here. So we see that is continually increasing on the left. Now, if we look at the right side, we're going to see that this graph is symmetrical about the point x equals 1. So as we approach x equals 1 from the right, we're going to get the same behavior of it continually increasing. So this sketch alone would potentially be enough to get the limit, but to make it a little clearer, I've plotted the function in Mathematica. And here we could definitely see that as we approach 1, it is continually increasing. And from the left side, so in particular looking up this arrow, we see that it's increasing continually. So we would say that it's approaching infinity. Similarly, on the right side of x equals 1, we see that it's also increasing continually. So the limit on the left side is infinity, and the limit on the right side is infinity. So we could say that the limit as x approaches 1 of 1 divided by x minus 1 squared would be equal to infinity. And again, that's because the limit on the left is infinity and the limit on the right is infinity. If either of these weren't infinity, then we would say that the value doesn't exist. Now let's try another example. So for the first thing we're going to do for this example is the same thing we've done previously. We're going to start by writing our function x plus 6 divided by x squared minus 36, and then we're going to plug in x equals 6. Doing so gives 6 plus 6 divided by 6 squared minus 36, which evaluates to 12 over 0. So now we have shown that it is undefined, and from there we're going to do what this list of steps I wrote said, and we're going to draw our graph. So we're going to first start off by drawing our blank graph and marking where we want x equals 6 to be. So now let's look at the values to the left of x equals 6, or the smaller values. We see that when we plug in a value such as 5, for example, we get 5 plus 6 divided by 5 squared minus 36, which is 11 over negative 9. So we see that's a negative value. As we increase the value but still have it less than 6, such as then 5.5, 5.9, we're going to see that our numerator is always going to be positive, and our denominator is going to be negative, but our denominator is going to approach 0. Since the denominator is getting smaller and smaller, the value of the fraction is going to be getting larger and larger. However, since we have the denominator will always be negative when x is less than 6, we see that this function evaluates to an increasingly negative number, less than x equals 6. So we see that this side of the graph will look like this. Now we're going to look at the right side, and we're going to try a value such as x equals 7. 7 plus 6 is 13, and then 7 squared minus 36 is also 13. So we see that we end up with a 1 for x equals 7. And then as we move to the left, but still say greater than x equals 6, so we'll use values such as then 6.5 and 6.1, we see that it will always be positive, both the numerator and the denominator. However, the denominator gets smaller and smaller. Again, when our denominator gets smaller, our fraction will get larger. So since it's a positive value that gets larger as you approach x equals 6, the graph is going to look like this. So now this graph should be sufficient for us to get the limit, but just for clarity, I've plotted it in Mathematica shown here. And now we'll look from the left and the right. From the left of x equals 6, we see that the function is continually decreasing, so the limit will be approaching negative infinity from the left. Similarly, on the right side, we're going to follow the arrow. However, this time we see that's continually increasing. When the function's continually increasing, we know its limit approaches positive infinity. So we see that the limit from the left is negative infinity, and the limit from the right is positive infinity. However, these values are not equal, and when the limit from the left are not equal, we say that the limit does not exist. So the limit as x approaches 6 of x plus 6 divided by x squared minus 36 does not exist. So now let's try one more example. So here we're going to find the limit as x approaches 0 of the natural logarithm of the absolute value of x. So you'll see that this is very different from what we've looked at in the previous two examples, but nonetheless, we could apply the same steps. So we're going to start by writing our function, the natural logarithm of the absolute value of x, and then we're going to evaluate that at x equals 0. And this gives us the natural logarithm of 0. As we said at the beginning of this video, the natural logarithm is only defined for values greater than 0. So here, this is undefined. So we're going to need to go to a graph to evaluate this limit. Now this is a complicated function, so we're going to graph this function as follows. The first thing we're going to want to do is graph it just greater than 0. And when x is positive, we could just rewrite this function as the natural logarithm of x for x is greater than 0. And when we do that, we know that the typical behavior of a natural logarithm graph is this. We see that it slowly increases infinity as x goes to infinity, and then as we get close to 0, it's going to continually decrease. However, now let's look at the negative side, which is a little less obvious. So the way I'm going to describe this is to look at the natural logarithm of the absolute value of negative x. Since the absolute value of negative x is just x, we're going to see that this is the natural logarithm of x. So we see that the left side of the graph, or when x is negative, it's just going to be a mirror image of what we have for the positive side. So our graph will look like this. And from here, we could easily figure out the limit as x approaches 0, but again, for clarity, here is it formally plotted. We see that for values less than 0, to find the limit, we'll look along this arrow here, and we see it's continually decreasing, so we know that its limit is negative infinity. Similarly, for the values greater than 0, we'll follow the arrow on the right side. And we see that it's also continually decreasing, meaning the limit from the right approaches negative infinity. Here, the limit from the left and the limit from the right are both negative infinity. So, since they're equal, we know that our limit's going to exist. And since they're both negative infinity, we could say that the limit as x approaches 0 of the natural logarithm of absolute value of x is going to be equal to negative infinity. So now that we've done all 3 examples, here are some extra practice questions for you to try on your own. The first one asks you to find the limit as x approaches pi over 2 of tangent. Problem 2 asks you to find the limit as x approaches 0 of 3 over x cubed. Problem 3 asks you to find the limit as x approaches 0 of 3 divided by x plus 4 to the 4th. And lastly, for problem 4, we have the limit as x approaches negative 3 of x minus 3 divided by x plus 3 squared. I would start off by trying to graph these functions on your own without a graphing utility, and then after you graph it on your own, plot it and check your work. The answers to these problems will appear in 5 seconds. Okay, so you should have gotten that the answer to the first 2 questions were both that they didn't exist, and that's because the limit from the left didn't equal the limit from the right. For problem 3, you should have gotten that the limit was positive infinity, and for problem 4, you should have gotten that the limit was negative infinity. I hope you got these. If not, feel free to leave any questions you have in the comments below. Thank you so much for watching. Have a great day.